In this class, we are going to discuss Poisson distribution problem. Okay. So I have already told you, just a minute. I have already declared that I'm going to discuss Poisson distribution. So you don't have to verify whether the problem is a Poisson distribution problem or not. I will give you such a problem, which are the problems of Poisson distribution, but I will only tell you why the problems are the problems of Poisson distribution. That I am going to tell you. Okay. And the first problem that I'm selecting is this. A car hire firm has two cars which it hires out day by day, day by day. The number of demands for the car, the number of demands for a car on each day is distributed as a Poisson variate. With not Poisson variate. Okay, I can write variate. I can write it is distributed as Poisson variate, or you can write it follows Poisson distribution. Whatever, it follows Poisson distribution with mean 1.5. Okay. Calculate the proportion of days on which number one, neither car is used. Number two, the proportion of days on which some demand is refused. Okay, so this is the problem. So already it is mentioned in the question that it is a problem of Poisson distribution. So generally, it is quite natural that we are going to apply the formula of Poisson variate or formula of Poisson distribution. But first of all, if you are solving the problem, you have to identify why this problem is a Poisson distribution problem. Why they have called this situation is a Poisson variate situation. It's a situation where random variable can be treated as a Poisson variate. What is the random variable here? So let us try to identify the random variable from the question. Random variable, if you go to the question again, you will find that the random variable which actually gives you the count is the number of demands for a car. The random variable is the number of demands for a car. Okay. So let us write, let X be the random variable which defines the demands demands for a car on each day or each day. Okay, that is the demand. Number of demand is actually our random variable, but the car hire firm that customers pour in to get the cars on rent, that firm has only 2 cars with them. And as a car owner, you don't know how this demand function is distributed. How this demand function means the random variable is distributed. I don't know that how many people are going to turn into my farm to book for the car. Okay, so that number of customers coming into my farm is not known to me. And when something is not known, because you see, other farms are there which have many cars than my farm. Automatically the customers will go to get the cars from there. But there are some situations where all the in a busy season, all the cars from other farms are booked. So some customers may turn into my farm to get the cars. But my only disability is that I have only 2 cars with me, not more than that. So, and I don't know that the number of customers coming into my farm is not actually uniform. It haphazard. Sometimes it goes one or 2 weeks, or I had to wait for 5 or 6 long weeks to get one customer. So this is the situation of my farm. They are telling. Okay, so I don't know what will be how many demands will be coming in to my farm. They have asked me to calculate to consider the situation as the situation of the Poisson variable. Also, if you say that, okay, I don't want to consider this as a Poisson variate situation, then automatically the question is that you know only 2 distribution. One is binomial and another is Poisson. So what will you do now? If it is not by Poisson variate, then do you want to apply binomial variate? But you cannot apply the binomial probability law over here, because in binomial probability, 2 things are required. One is the number of experiment and the probability of success. Success is defined, demands coming in. Okay, how many demands, how many times you are experimenting, how many days you are looking for the demands, that is not sure. We are not sure about it. The probability of success, we are not sure about it. Only one thing is given, that mean on an average, this particular random variable has average value, which is 1.5. So N and P are separately not known. What is known is 1.5. Now, what is this 1.5? Since it is given in the question, that X follows Poisson distribution, and we know that expectation of Poisson variate is actually equal to lambda, which is NP. That is mean of the Poisson variate. And therefore, this mean is given over here, which is 1.5. So the lambda is known to us. The parameter of the Poisson variate is given to us, which is 1.5. Now, since it follows the Poisson distribution, and we know that capital X be the demand for the car, the probability that there will be exactly small x demands is given by probability of x equal to small x e to the power minus lambda, lambda to the power x by x factorial. X is equal to 0, 1, 2, infinity, up to goes on. If you have gone through my video in the last yesterday's video, then you will understand what this e to the power minus lambda. E means the exponent, lambda is the mean, as you already know. X is the values, probable values of capital X, and 0 stands for no demand. I mean, in this case, it stands for no demand. A particular day is there when there is no demand, and it goes up to infinity. Binomial distributions case, the variable X takes values from 0, 1 to up to n. This is finite in binomial probability law. But in Poisson probability law, this is not finite, this is infinite. That is another difference between Poisson and binomial. Number one question is that, what was the question? Let us see. Calculate the proportion of days on which neither card is used. The probability, first of all, let us try to find out the probability. Probability that neither card is used, neither card of my farm is used, it means that there is no demand. That is probability of x equal to 0. And this is equal to e to the power minus 1.5, because lambda is 1.5, 1.5 to the power 0 by 0 factorial, which is e to the power minus 1.5. You can calculate this exponent using calculator, or you can keep it as it is, no problem. Okay, that is the probability, and probability is the, actually, if you calculate the probability, can anyone say what is the value of e to the power minus 1.5? You can write in the chat box. 0.2231, 0.2231. So proportion of days in which neither card is used is 223 out of 1,000. 1,000 days, you are observing the situation for 1,000 days, 223 times it will occur that no card has been used. It depends upon, if you are talking, if you take only 22, if you retain 2 decimal points after 2 digits after the decimal point, if you retain up to this, my conclusion will be, if I repeat the experiment for 100 days, 22 times the situation will occur. I am retaining the decimal point up to 3 digits, then I will say that the proportion of days will be 223 out of 1,000. If you retain more decimal points, we accordingly will try to give your conclusion. Okay. Number 2 is the probability that some demand is refused. The probability that some demand is refused. What does it mean? It means that the demand for the card will be refused by the firm only if the demand exceeds 2. All your cards are out of the firm, they are booked, and then another demand comes. Only 2 cards you are having, and the 2 cards have been booked. Another demand has come in, so you have to cancel that demand. So that demand must be greater than or equal to 2. And this, if you try to calculate this probability directly, you will not be able to do so, because in that case you have to write probability of x equal to 3 plus probability of x equal to 4 plus probability of x equal to 5 and so on. You don't know how far you have to go. It's infinite. But you can apply the complementary event probability over here. I can write it as 1 minus probability of x less than or equal to 2. And this is probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2. Okay, and subsequently you can put all these values of small x 0, 1, 2 into this formula. So we can write e to the power minus 1.5, 1.5 to the power 0 by 0 factorial plus e to the power minus 1.5, 1.5 by 1 factorial plus e to the power minus 1.5, 1.5 square by 2 factorial. Or you can further simplify, you can take e to the power minus 1.5 common, and you can write it as 1 plus 1.5 plus 1.5 whole square by 2 factorial. Okay, so this, and you calculate this probability, and accordingly you give your conclusion about the proportion of days in which their demand will be refused. Okay, so this gives the solution of the given problem. This is page number 2. So I'm going to the next page. Let's solve another problem. Okay. Example 2 is that suppose that number of telephone calls, telephone calls coming into a telephone exchange, between 10 a.m. and 11 a.m. Say X1 is a okay, after say there will be no comma, sorry. You know, say capital X1 is a random variable with Poisson distribution with parameter 2. Okay. And similarly, the number of calls arriving between 11 a.m. and 12 noon, say X2 has a Poisson distribution, with parameter 6. If X1 and X2 are independent, if capital X1 and X2 are independent, what is the probability that more than 5 calls 5 calls come in between 10 a.m. and 12 noon. 10 a.m. and 12 noon. 10 a.m. and 12. So this is a problem, and I have selected this particular problem for a special case, because you see this problem is special because there are two random variables involved. One random variable is x1, which counts the number of calls, but in a time frame 10 a.m. to 11 a.m. with a parameter 2 following Poisson distribution. And another random variable is x2 in the time frame 11 a.m. to 12 noon with a Poisson distribution with parameter 6. Now we are supposed to find the probability that more than 5 calls come in between the entire time limit 10 a.m. to 12 noon. Okay, here we are going to apply one theorem. That theorem is very important. Problem you can easily solve, but the theorem is very important. The theorem says that if capital X1 follows Poisson distribution with parameter lambda 1, I'm writing in symbol, and X2 follows Poisson distribution with parameter lambda 2, then the random variable x1 plus x2 follows Poisson distribution with parameter lambda 1 plus lambda 2. It's a theorem, and this theorem is very important. Okay. So rest is very simple. You can do it by yourself. That we shall write that everything is defined properly. That capital X1 is the random variable with Poisson distribution with parameter parameter 2. You will first write what is given. Okay. So here in this particular case, X follows Poisson distribution with parameter 2, and X2 follows Poisson distribution with parameter 6. Then you will write that X equal to X1 plus X2 is denoting the number of calls received in the entire time frame, or you can write from 10 in the morning to 12 noon. Okay. Then X1 plus X2, you can name it as capital Y. Okay, for simplicity, this follows Poisson distribution with parameter 8, and your job is done. Now you will write that number of calls, the probability that Y calls will be received. Y calls will be received is probability of capital Y is equal to small y, which is e to the power minus lambda to the power y by y factorial. Y takes value 0, 1 to up to infinity. Now we are supposed to find the probability that more than 5 calls come in between 10 a.m. and 12 noon. So the probability that more than 5 calls come in between 10 a.m. and 12 noon is probability of y greater than or equal to or greater than 5, more than, it is said more than, greater than 5. You can write it as probability of 1 minus probability of y less than or equal to 5. And after that, what you can do? You can write it is 1 minus summation y goes from 0 to 5 e to the power minus 8 to the power y by y factorial. This is your required answer. If you wish, you can calculate this, or if you don't want to calculate, then you can skip it as it is. Okay, it's up to you. Now, if this problem comes in the online examination, the value, probably they will calculate this value, and after by subtracting the value from 1, they will get 1 result. They will give you the results. So you have to calculate. You have to take the pain of doing that calculation over there. Okay, let's solve another problem. Okay, what? Someone saying something? Okay. Priyadarshi CSC raised his hand. You want to say something, can write in the chat box. Priyadarshi, want to see the page? You raised your, oh, okay. So another problem, a manufacturer who produces medicine bottles, finds that 0.1% of the bottles are defective. The bottles are packed in boxes containing 500 bottles. Okay. A drug manufacturer buys 100 boxes from the producer of bottles. Okay. Using Poisson distribution, find how many boxes will contain no defective, and number 2, at least 2 defectives. Now here, the situation is a little bit different in the sense that, see, this particular problem can easily be done by binomial probability laws. Try to look at the scenario very carefully. Finds 0.1% of the bottles are defective. 0.1% of the bottles are defective. So if I define capital X to be the random variable counting the number of defective bottles, then probability, then the success is defined to be the situation when a defective bottle is found. And probability of success in this case is equal to 0.1%, which actually means 0.1 by 100, that is 0.001. It is the probability. And you see that it is written that the bottles are packed in boxes containing 500 bottles. Okay, so this 500 is actually your small n. The number of boxes packed, with apparently these defective bottles is equal to n, which is 500. Now I could easily solve the problem by binomial variate, but it is mentioned that you have to prove it by Poisson variate, because they have asked you that using Poisson distribution you calculate this figure. So we are left with no other choice, but we know that with respect to if I compare these two terms, 500 and 0.001, these are 500 is too large and 0.001 compared to that is too small. So probably this particular problem can also be done by Poisson distribution case. Yesterday I told the students that there may be the situations where one particular problem can be done by both of these probability law. Okay, try to go through the video today in your leisure hours. And then I shall upload my today's class later at night. So you're not going to get the video right now. Watch the previous one, and then if you watch it, everything will be clear to you. Now, how to calculate the parameter lambda? Because we know the Poisson distribution has parameter lambda. The parameter lambda of Poisson variate is NP, which is 500 into 0.001. How much? Can you calculate how much is coming? 500 into 0.001. Anybody please write in the chat box. 0.5. And so we have got our lambda. Now we want to find the defective. First of all, we are going to find the probability of defective bottles. The probability that small x bottles will be defective is probability of x equal to small x, which is e to the power minus lambda to the power x by x factorial, or e to the power minus 0.5 to the power x by x factorial. X runs from 1 to up to infinity. Now they have asked to calculate The probability, first of all, there will be no, what is the probability that there will be no defective? The probability that there will be no defective bottles, is probability of x equal to 0, which is e to the power minus 0.5. And number 2, the probability that at least 2 bottles are defective is probability of x greater than at least 2 bottles, x greater than or equal to 2, which is 1 minus probability of x less than 2. Okay, and this is 1 minus probability of x equal to 0 plus probability of x equal to 1. Now you have found, I'm not going to calculate these probabilities, you can very well find it. But what is actually required? The actual requirement is the how many boxes will contain no defective items and at least 2 defective items. So then lastly, you have to write that the number of boxes containing no defective bottles See, a drug manufacturer buys 100 boxes from the producer of bottles. So this 100 is significant. That is capital N. That the number of counts gives the number of bottles that is being bought from the manufacturer. Okay, so number of bottles containing no defective, number of boxes containing no defective bottles will be calculated by multiplying the probability of no defective by the quantity 100, and the probability, the number of boxes containing at least 2 defectives will be obtained by multiplying 100 by that probability, 1 minus probability of x equal to 0 plus probability of x equal to 1. Okay, I shall recommend this particular problem for binomial variable case also. So your job is to try to calculate the probability with binomial probability law also and see the difference. This is your homework. So this is page 2, this is page 3, this is page 4, that is page 5. So today I'm going to stop my session at this stage. We are going to meet again tomorrow in the afternoon session. Okay. So I'm stopping the recording right now. This much for today.